Today we're going to talk about how Valve has been using deep learning to effectively combat cheating in CSGO, which is a bunch of words, and we're going to unpack them now. We're going to cover a bunch of stuff. Basically, we want to do an introduction, and then I'll give sort of the elevator pitch of that I sort of gave back at Valve in 2016 when I was like, hey, we should do this thing. Maybe it'll fall over. We'll find out. Spoiler alert, it doesn't fall over. It works really well. And then we'll just jump into the results that we got. We'll talk a little bit about training, which probably is super unnecessary, but good news, it's only one slide. And then we'll talk about how we actually sort of feed our neural net and some stuff that's going on. And then conclusion if we have questions or anything. All right, so let's talk a little bit about CSGO itself. CSGO basically is a competitive multiplayer first-person shooter. We have about 12.4 million monthly uniques, and about 3 million folks check in with us every day, or 3 million uniques check in with us every day. It's the 10th title that ships on the Source engine. The first was Half-Life 2 back in 2004, and that's sort of relevant, as we'll get to in a little bit, because it affects the sort of ease with which somebody can cheat in CSGO. The combat engagements in CSGO are short and really brutal, and the bullets, that's because the bullets are very, very lethal. The engagement time on average is sort of 1 to 2 seconds. They're very fast. This is that slide. And I'm gonna, just before we talk about competitive CSGO, we are gonna just briefly try and play this video and see how it goes. Okay, so this is actually, because I figured you guys might not know, this is basically what competitive play in CSGO looks like. This is this player, Skadoodle, from a sort of, he's a professional CSGO player. This is from the most recent tournament, and we're just gonna watch, he's gonna throw some utility. I'm more or less gonna let this do the talking for me, but one thing I wanna sort of point out is to watch sort of how short and brutal the combat is. So he managed to headshot that guy. That guy died in one hit, even though he started spraying a little earlier. He's checking some angles. He's worried about somebody coming this way. There, he's just got another kill. There's that guy from that angle. He's going to hold an angle here for a little bit. He's looking for somebody to come pick him off. They know where he is. There's one more, and there's the last one. This is from, Skadoodle plays for Cloud9. They actually just won the most recent tournament, so they're currently the best team in the world. Okay, so that mode that Skadoodle was playing, and the mode that most of our players, or that our players spend a lot of time in, is this 5v5 competitive mode, where you basically play sorry about that. Oh, that is unfortunate. Okay, where they spend the bulk of their time. There we go, that's better. Each round is basically 2 minutes and 57 seconds long. We round up to 3 minutes, and so when you sign up for a matchmaking session, you agree that you are going to be locked in a room with somebody for up to 90 minutes. In fact, you're going to be locked in a room with 9 other people for up to 90 minutes. You can't voluntarily leave a match in CSGO without a penalty. You can be forced to leave either by being kicked, and you can abandon a match, and both of those will result in you receiving some sort of punishment, usually a ban, like you were just prevented from matchmaking for a while. The average game basically is around 40 minutes, and 65% of our players basically play at least one competitive 5v5 match per month. And there are about 600,000 5v5 matches a day. So, all right, cool. That's CSGO. Let's talk a little bit about cheating in CSGO. In 2016, when I started this work, cheating was kind of the largest problem that players would talk about. In fact, it was pretty much the only problem they would talk about. If you looked at the Reddit forums, the Reddit threads, or if you looked at the contact alias that we have, like we have a CSGO team feedback at valvesoftware.com, and anybody can basically send us mail or feedback about the things that we're doing right, or usually the things that we're doing wrong. But we do actually get some mails where people are telling us, hey, you're doing a good job. Those feel really nice. The thing is that probably, and I actually pulled statistics at the time, but I don't have them anymore, but it was about 95 to 97% of the mails were basically, your game is filled with cheaters. Why are you not doing anything about the cheating problem? And so this was like the only thing, like I couldn't figure out anything else to work on other than cheating. But we weren't actually sure whether the problem was actual cheating or whether the problem was just this perception of cheating. We did have these bans. We'll talk a little bit more about what VAC bans are in a bit, but basically we had some data about bans that we were handing out for cheating that supported that this probably was an actual problem. It probably wasn't just a conversation about the problem. And if you think about CSGO and what you've just seen, there's a couple of things that kind of make it sort of reasonable why CSGO would have such an aggressive problem around cheating. And one is that the design, because headshots are so damaging, almost every weapon in CSGO actually can kill a player with one shot as long as it's put in the right place. So our weapons are extremely lethal. And then the sort of having any informational advantage over your opponent just makes it, just really magnifies your advantage in any particular encounter. But the other problem, and so that's one problem, the design sort of fails to disincentivize cheating. And we don't really think that's a problem overall because the game is super fun. I don't know if any of you are players, but the game is actually really fun. It's very rewarding and getting kills feels like great. But there is this sort of cost that we pay for that sort of solid feeling. The other problem, though, is that the engine itself is, because it's so old, like the bulk of the code for CSGO actually dates back to, like I said, Half-Life 2. And that kind of means, like, which was released in 2004. So that means that if you have a cheat that was written for, say, Half-Life 2 Deathmatch in 2005, that cheat, if it gets posted on GitHub, probably works in CSGO today with a relatively small amount of code change. And that's kind of terrifying. Now, the good news is we actually do catch almost all of those old cheats. And actually, at any given moment, we probably catch approximately all of them, but they show up, even new ones, every so often. It takes a little bit to catch up. There are a couple of main types of cheats in CSGO. They sort of fundamentally come down to cheats that are like aim assistance. It helps you aim, and cheats that give you information that you shouldn't have. And those tend to be wall hacks, like I disable the rendering of this wall, and therefore I can see a player coming around. Or a lot of the common cheats tend to just draw bounding boxes around enemy opponents and then draw them with a different shader if they're behind walls so that they still show up. And they draw that as an overlay on top of the game. Now the aim assistance cheats, the aim assistance cheats tend to just be basically ways to make it easier to actually get the kill that you want to get. And this goes back to that game design problem that I was talking about before. A game like Dota doesn't really suffer from cheats because the complexity of communicating your intent to a cheat is the same as the complexity as just indicating to Dota what you want to do. In CSGO, like the thing I want to do is I want to kill that guy that just showed up on my screen. And so if I have a cheat, maybe I just press the X key and then that guy dies. Whereas if I don't have a cheat, what I need to do is like move my mouse over to his head and then start pressing the button. And then I need to counteract the recoil pattern that's going to have and try and spray him down. That was one of the things Skadoodle did on that very first kill. Like the way he was pulling his gun down was him counteracting recoil. And that's obviously a lot more complex than just press X and the guy dies. Now, there's sort of a spectrum of cheats that show up sort of from, and we kind of think of them as like how obvious the cheats are. So, subtle cheats are sort of, and a lot of times, not really noticeable at all to sort of an outside observer. But we also have, and then there's sort of cheats that are obvious, and then we have these cheats that are sort of way out here on the edge that we call rage cheats. And the goal of a rage cheat is not to appear to be better than you are. The goal of a rage cheat is to enrage you. I want to piss you off that we are locked in a room together for 40 to 90 minutes. I actually, as the cheater, get to control exactly how long the match is going to be, and you're stuck here with me, and there's nothing you can do about it. And so my goal is just to piss you off. I want to ruin your day. Those are a special type of cheat that are just super fun. So Now, the problem is because of that 5v5 game mode, and like I said, like once you sort of agree to go into the matchmaking queue, you're locked in a room with 9 other people. And so imagine that you're a totally clean, legit CSGO player. There are actually tons and tons and tons of you. But the problem is that it takes only a very small amount of cheaters in the pool in order to basically ruin your games. Like, for example, if you have a base rate of cheating that is 2%, then 10 of your matches are going to be dirty. Oh, this 4% should be 3 of 10, sorry. Anyways, if you have a base rate, if 2% of your players are cheaters, then 2 of 10 matches are going to be tainted. There will be a cheater. Given that you are a clean player, one of the other 9 players is going to be cheating. And what's a little worse about that is that because you're clean, that means that you are more likely to face a cheater than to have a cheater on your team. Because there are only 4 slots for a cheater to land on your team, and there are 5 slots for him to land on the other team. Or her, I don't discriminate. Could be, it could be a female player as well. Now, if you're at a 7% cheating rate, almost 50% of your games are gonna have cheaters. That sucks a lot. Now, the good news is that it's not as dire as all this. Because we have this system in place that we deployed last year called Trust Score. And what we do is we basically trained a model to sort of look at the ways that you interact with CSGO and the ways that you interact with Steam. And then we basically match players. Oh, and we predict whether or not those players, based on those interactions, are going to go on to receive a ban. And then what we do is we use that system to predict a score that basically says, like, how trustworthy are you? And we match people with similar trust together. And that lets basically our known good actors play with other known good actors, which means if you are a good actor, you run into cheaters a lot less often. All right, so this is probably actually a little bit easier to visualize than it is to describe. So this is a field of 50 players, and their position in here doesn't matter at all. But we need to divvy them into 5 competitive matches. So because PowerPoint drawing is hard, we might divide those matches up like this. And so now we've created 5 matches, and all these players have probably similar MMRs, so we could have drawn this any way we wanted. But let's see how we did. So we have this system we'll call the rainbow of trust. And the idea is that the red players are likely to go on to receive a ban. Like, they're pretty likely to go on to receive a ban, while the blue players are very unlikely to receive a ban. Somebody who's got 400 games in their Steam catalog and has played for 50,000 hours cumulatively, that person probably is not actually going to cheat, or they're really, really good at it and they deserve to win. No, that's terrible. I don't mean that at all. The problem here is that if we assume even half of these red players are cheaters, then in principle, like, all of these matches could have cheaters, and these matches suck for everybody. So with trust, we could instead consider that when we're doing matches as well, and we could draw our matches like this instead. We still have 5 matches that we've created, but now our blue players are very unlikely to play with our red players. And in fact, here we've probably created 4 really high-quality matches, so this is pretty good. Now, you might be asking, well, if the red players are dirty cheaters, why don't you just ban them? And the answer is, they haven't cheated yet, as far as we know. They're just much more likely to go on to cheat. And we have a bunch of data that trust is working really well, but I kind of prefer the anecdotes instead. We rolled trust out about 6 months before we said anything about the fact that we rolled it out. And during that time, we were paying attention to the community forums, like on Steam, and we found that these threads would show up where somebody would say, this game is filled with cheaters. It's terrible. Like, I run into cheaters every single game. And then there'd be a bunch of replies from people that would say, I don't know what you're talking about. I never run into cheaters ever. And you'd go and you'd look at their trust scores, and you're like, the guy who was complaining is like, hey, he has 49 accounts, or he has 50 accounts, and 49 of them have been banned for cheating. I don't care that that guy plays with cheaters. I want that guy to play with cheaters. That guy is a cheater. He is ruining tons of matches. And you look at the other people and you're like, yeah, these look like good, wholesome CSGO players. The system's working great. So we finally, clued the community in that, hey, we're doing this thing to try and help you run into cheaters a little less often. And that's a thing that's probably worth mentioning about trust. This is kind of the last we're going to talk about trust. But trust doesn't reduce the rates of cheating for us. It just reduces the blast radius of cheating so that it sort of mitigates some of the damage that cheaters can do. All right, so let's see here. So we're going to talk a little bit about the anti-cheat, existing anti-cheat that we have on CSGO. So the sort of two primary forms of anti-cheat that we have already are basically mitigating exploits and VAC. And I talked a little bit about VAC before, Valve anti-cheat, and now we'll go into it in a little bit more detail. So mitigating exploits is basically like, Valve, fix the servers, please, fix the game. We do that work all the time. And in fact, like that is the probably most common work that we do on the team is fixing these kinds of problems. It's always an option. We're doing it all the time. You know, an example is like we had this case where users realized that they could modify a timer call on their operating system, its query performance frequency, if you're a programmer, and they basically could convince the client that it was running really, really fast. And so then what it would do is the client would send server commands to the server and be like, hey, here's a bunch of movement commands. And the server was like, I trust you, you're good people, and it would honor those movement commands, and it would often get like 10 movement commands when it only expected 1. When it didn't do anything, it just processed them faithfully. And this would result in those players basically just teleporting around the map, which is super, super unfun to play against, as you might imagine. The net effect of this, I mean, the fix was really, really straightforward. It was probably the fix that you would imagine. This is a little hand-wavy, but basically it's like, I'm only gonna pay attention to 1 movement command per client per tick. And the problem pretty much, you know, solved itself. Now, one of the things that's worth mentioning is that as we do this work, bad actors evolve. So we make changes, and then they make changes, and then we make changes, and they make changes. And this evolution results in this treadmill of work for our developers. And that was the thing that deep learning was really interesting to us about. Now, VAC is the other sort of thing that we do. There's basically client-side detections and server-side correlations. And it's only active when you're connected to a VAC-secured server. And the evidentiary standard for VAC is 100%, with a caveat. Sometimes we F up, right? And when we do, we fix those mistakes immediately, and we're very clear that we made a mistake. We make sure that there's a blog post about it, and we roll back the bans, and we talk about what the problem was and how it won't happen again. And the great thing about that is that as a result, our community has pretty strong belief that VAC is doing the right things. Or said differently, when VAC takes action and somebody is banned as a result of VAC, our players believe that that person was cheating because they were. Now, talking about VAC is a little tricky because when we talk about VAC detections, it prevents them from working. You know, so if I tell you, for example, hey, what we do is we monitor processes that are writing into our process, and if they're fiddling with our memory, we figure out what their bytes on disk are, and then we check some of those bytes, and then we phone that home, and we check it against the database to figure out whether it's like something totally harmless like OBS, or whether it's actually something more nefarious. When I tell you that that's a thing that we did, I lit that thing on fire. Like if somebody is live tweeting now, that thing won't work by the end of the day. Actually, as a point of full disclosure, it won't work as of Thursday last week, because that's when I first talked about it. But the good news is we have thousands of these detections, sort of various sophistication, and we work on them every day. But the problem, again, is that bad actors evolve. We write new detections, and then that evolution, and then the bad actor you know, comes up with new work. And this isn't like a theoretical concern. We have had sort of cases where somebody has said something as minimal as, I can't wait to see what happens to cheaters because of this new detection. And within 3 hours, a cheat developer had reverse engineered the new detection, and it didn't work anymore. Like we started just like the number of detections on that just went to 0. So again, bad actors evolve. The evolution results in a treadmill of work. And one of the things, again, that's sort of worth mentioning about VAC is like VAC has a client component and a server component. Okay, so let's get to the elevator pitch on like why deep learning might be a better, better attack for this, or at least a good attack for this. But before we do that, I'm going to do the thing that I totally don't need to do for you guys, but let's just talk about the 40,000-foot view of what deep learning sort of is doing. right? Deep learning is going to basically build the possible functions that maps inputs to outputs. And because I think you guys are all sort of familiar with this, spoiler alert, we're really talking about supervised learning here when we're talking about this. So we have, basically, you're familiar with the algebra notation, y equals f of x. And what I like to think is that deep learning basically just says, hey, given enough x, or at least supervised learning says, given enough x and enough y, we could solve for f. And that's pretty cool, right? So then we can apply our f to never before seen x, and we get sensible y. And if we don't have deep learning, engineers write that f. They're on the treadmill. And for Valve, this means that we can trade data and compute for engineering time. And we're a company that is perpetually resource constrained in terms of humans, like the humans that can actually sit in front of a keyboard and type things out, or artists that can art, or level designers that can level design. That is the thing that we are always short on. So this ability to trade data and compute for engineering time, we're huge fans of. Now, concretely, and I'm going to do this, even though I know everybody here knows it, we're going to have a little metaphor for deep learning. And I kind of like to think basically of making hamburgers. So if I had cubes of meat and I had delicious hamburger patties, then I would expect deep learning, given enough cubes of meat and enough hamburger patties, to basically build me a meat grinder. And so we're gonna stick with this metaphor. I'm sorry to the vegetarians, I apologize. Now, I mentioned that we're only going to build a possible function. That's the word we're going to highlight over there. And that's basically because, as probably all of you know, we're only going to get one possible sort of function. But in terms of f, there are quadrillions and quadrillions of different f's that would all satisfy this equation. Now, given enough data, there probably is a closed form or nearly closed form solution for f, but we will never have that much data. So we're happy to get just one of the possible functions. Let's see here. Deep learning is good at things that you guys know about because you all know, but there's my cat sitting on a sofa, and deep learning would totally tell me that that cat was sitting on the sofa. It operates in two modes, as everybody here knows. So for training, we're going to talk about how we build a meat grinder by showing cubes of meat and hamburger patties. And then inferencing, we're going to use that created meat grinder to turn sort of never before seen cubes of meat into patties. So given that I trained it on beef and pork, and then I'm suddenly like, hey, here are some cubes of chicken. I expect to be like, here's a chicken patty. You'll totally like this. It totally won't make you sick as long as you cook it well enough. I may accidentally slip into saying machine learning. I don't know that I need to explain this to anyone in the room, but sorry, I already did the slides. And this is sort of the relationship between the two. Deep learning is the small circle, machine learning is the big circle. That may not be technically accurate. You can totally tell me why I'm dumb and that's wrong later, but it totally worked for game developers, so. Sorry. Deep learning is still super new to game developers, so audience level is a little bit lower than probably what's here right now. Just in terms of deep learning experience, they're all very smart. Okay, so let's get back to our elevator pitch. So the notion basically we had is that humans watching matches can tell that cheating is occurring. They're detecting patterns of cheating, right? And we don't know what the pattern is that they're looking for, but they're doing some sort of pattern matching. And deep learning is really good at detecting patterns, so shouldn't deep learning be able to detect cheating? Aimbots seemed to us like the biggest problem and the loudest signal, so we thought that we would target those first. Those like rage bots that are using aim assistance, we were like, let's go after those first, because that signal seems super loud. Now, if you recall, we said that deep learning is solving y equals f of x for f, if only we had x and y, which it turns out we did. We built it several years before, and we didn't even know that that was the thing that we had built. We built this system called Overwatch. And Overwatch is no relation. Overwatch is a jury review system where players basically watch cases, they decide guilt, and then they render a verdict. And then we record all of that forever. So the process basically works like this. Players report players, and then the coordinator selects cases. Players adjudicate the cases using a process where they sort of watch demos, and they're watching an 8-round snippet of a game. And then they're basically asked, is there evidence beyond a reasonable doubt in each of 4 categories? And then if enough players vote guilty, then they're banned from CSGO. If they're not guilty, there's no punishment. The person just goes back in. Now, the Overwatch process itself uses a naive Bayes model to sort of figure out the guilty threshold, and that makes it really easy to acquit players and hard to convict, which we think is really important. We think it's really important that we not accidentally convict somebody who is, not guilty. The evidentiary standard that we're shooting for is basically 99.8% as decided by your peers and the naive Bayes model. And we can take a look at how we're doing. So we launched the system actually in 2013, but we didn't start really bringing it out of beta until much, much later. So this here is 2015. And in March, we started doing some work of 2015. We started doing some work that basically increased participation. And so if you unpack this graph a little bit, this gray line at the top is sort of the total number of cases adjudicated. And then the blue line are dismissals, and the red line are convictions. And we're going to use this graph a few more times. So that might be worth storing away for a little bit. The thing that's important here is that as we saw like, hey, this is great. As more people are participating, we're getting more convictions. We should get more people to participate. So we, Overwatch, we did the work. Overwatch leaves beta, and participation winds up being incentivized. And our conviction rate was abysmal. We did not actually get more convictions as a result of the increase in participation, and we were sad. And that was basically the state of things sort of at the end of 2016. So the things that we learned about Overwatch were that it helps with really blatant cheats, but it doesn't handle subtle cheats as well. And our problem did not appear to be that we didn't have enough people doing Overwatch. Our problem seemed to be that we were not putting the right cases in front of people. Now, the good news is humans don't appear to falsely convict, and that's been hand-reviewed a bunch of times. And bad actors basically evolved. Like, they got convicted by Overwatch, they would buy another copy and come back. But the good news is jurors do the same thing. They evolve as well. So here's the pitch. Let's get some deep learning up in this. We're going to basically take VACnet, and we want to train it from Overwatch, because we built a data labeling service on accident, and it's great. Then we're going to basically use VACnet to monitor matches. It's going to submit cases, and then we'll let humans decide ultimately, was this actually a cheat or not. So if you remember our existing sort of Overwatch pipeline, we just have to slot VACnet in here. VACnet's going to report players, and then the coordinator will just select cases. Oh, and I didn't mention it before, but the coordinator is just a machine. Like, it's just an algorithm that runs on the server that also does matchmaking and economy and other random stuff. Okay, so how'd we do? Okay, so if you remember, these were our results going into the end of 2016. The gray line is total, the blue line is dismissals, the red line is conviction. So what we did see was that, like, hey, when we rolled out VACnet, we don't actually see much of a change in participation. Like, we did get a step up for a little while, but to be honest, this kind of just looks like a product launch. Like, there's a bunch of participation, and then it sort of asymptotes down to whatever sort of normal level you kind of expect. So we think there's probably not anything particularly interesting here. But what we did see is our conviction rate started going up. Like, it actually started going up a lot. We were really happy about that. And then, basically, we kept accumulating data, we had more data, and we would retrain. And at this point, we were like, hey, this thing works. We probably should replace some of the gnarly placeholder code with, actual production-ish code. So we didn't actually get back to retraining for a while until the conviction rate started to seem like it was falling a little bit. But in November, we finally crossed our break-even point, where now our overall conviction rate is greater than our acquittal rate. And the story is actually a little better than that. It turns out that when a human submits a case into Overwatch, they only get a conviction about 15 to 30% of the time. This varies on a ton of factors, like the time of day of the week, the time of the year, is the game on sale? Like, there's just tons of factors that sort of determine what the sort of variance is. VACnet convictions are like 80 to 95% of the time. And it varies on roughly the same factors, with one exception. VACnet also basically has effectively a 99% conviction rate, like right after we retrain. That usually lasts for a few days. All right, so let's talk about how we train things. You guys know how to train things, right? You need we're doing supervised learning. You need to gather lots of XY data, you need to fit it, and then repeatedly be like, hey dude, how are you doing? And then when the model stops getting better, we're gonna save it for inferencing later. We actually been using Keras, and for game devs, I recommended Keras as well. we've had tremendous success with it. All right, so let's talk about care and feeding a little bit here. All right, so recall that our metaphor is this meat grinder. And what we need to do is feed it cubes of meat. Now the problem is, as game developers, we don't have cubes of meat. The problem is, as game developers, we have cows. And so just like with the metaphor, the overwhelming majority of the work involved has nothing to do with deep learning. The overwhelming majority of the work is how do I turn a cow into a cube of meat? And that is all just bog standard engineering work. And roughly, 95%, like I kind of went back and looked through my Perforce history and thought about all the time that I spent, and 95% of the effort was like, how do I get these cows to look like the cubes of meat that I need? 1% of the effort was around like actually turning the crank. That was like training the model and then deploying the model and feeding the model the right way. And 4%, the model, it breaks down a little bit here. The metaphor is a little bad there, but it's all good. If you are a game developer, the systems that you're going to basically need are a replay format. Which is basically a way to say, hey, like somebody has played a game, they've played a session, and now I need to know like what it looked like. What did the server think that their session looked like? And so I want to be able to replay that, right? That's really important. Then you're going to need to be able to store and fetch, transmit those replays. You're going to manage metadata around the replays, like what players are in a particular replay, and what was the score, and what map did they play on. There's a bunch of just sort of random stuff. That is like kind of the bulk of the things that you need. Ideally, you need a data labeling service. Now, I do actually think, I had somebody ask me at GTC, like, do you really need a replay format? Could you just instrument the server instead? And the answer is, yeah, sure. Like, I think you definitely can. Like, that'll make training a little bit harder, but for inferencing, I don't see any problem with that at all. And the other sort of thing is, like, I'd say ideally you need a data labeling service. I actually think that there's an approach to do this that doesn't require a data labeling service at all, but I don't have results for it yet, so I'm not quite ready to talk about it. So maybe I'll be back next year to talk about it, or I'll just have a poster among with the other posters. That'd be great. Let's talk a little bit about our data herd for CSGO. If you recall, I said basically we have 600,000 5v5 matches per day, and there's roughly 4 minutes of work per 5v5 match. About 3.5 minutes of that is like cracking the demo and building inputs for the model. And then there's about 30 seconds of random stuff, and then there's like 100 milliseconds or something to actually inference. Now, if you do the math, that is about 2.4 million CPU minutes of work per day, but there are only 1,440 actual minutes in a day. So you need like 1,700 processors to keep up with that. So that's what we did. We bought a bunch of processors. We actually, what you're looking at here is actually VACnet. I went with the ops team and installed this in one of our data centers. These two machines, I installed them with my own hands. Spoiler alert, like we went and installed this hardware 4 days before my wife gave birth to our second child. So I delivered my baby, and then my wife delivered our baby. It was awesome. Like, that was a race to the finish. That was a terrifying time. It was like, am I going to finish before? Because I wanted to accumulate all the data while it was out, right? I thought it'd be really helpful. Anyways, what you're looking at here is basically 2 chassis. There's 16 blades per chassis, and then there's 54 cores and 128 gigs of RAM in each blade. And we only use this for inferencing. The training actually all just happens on 1080 Ti's that sit under our desks. And then this is only 2 of the 4 chassis. The other 2 are in another data center. And we have them over there, for future expansion and also disaster recovery, right? So there's about 3,500 total processors between these 2 machines. All right, so I have 11 minutes. We're going to move quickly, and we're going to talk about the specifics of what we actually use to detect cheaters. Now, you guys all know I got to feed that learner in a very specific way. The sort of meat that I'm giving up needs to be uniform and fixed size. I don't think you guys care about this because I think all of you know what I need to do. So recall that we're basically specifically targeting aim assistance first. And aim assistance expresses cheatiness, basically, I think, if you logically think about it, when like bullets go downrange. So if I'm using aim assistance, probably most of the time I don't need to do anything, and then I press X, and then the thing locks onto your head, and it fires for you, and then you die. And so we basically decided to sort of focus on that first. Part of the reason that we focused on this first is we actually built a random forest before we had enough data. That thing worked pretty well too. But so we're going to basically build this little atom of stuff. And so the first question we ask is like, what weapon did you use? Were you using an OP or an AK-47 or an M4A4 or a pistol? Because those are, despite the actual weapons in CSGO, you're probably using one of those. Then that's good, there's one player, I know who you are now. Then there was basically, what was the result of the shot? Was it a headshot? Did you get a hit but somewhere other than the head? Was it a miss? And then how far away was the target if it was a hit? Then we basically take the delta view angle pitch. So this one requires a little bit of unpacking. And basically what we do is we say, for a half second before you took a shot and up to a quarter second after you take a shot, what was the delta view angle on each of those ticks? But we're only caring about how much you're sort of leaning forward. And we take all of that stuff and we feed it in. Then we do the same thing for your left to right movement. We just want the delta of your sort of left to right movement in this window of time. And we're going to take all that stuff and we're going to stuff it in. So that's it, right? Not really. That's just all of the properties of one shot. But we actually need a bunch of shots. Like, we need a lot of shots. Because in 8 rounds, players fire a lot of shots. So we actually need like 140 shots. And I apologize, this is not really, really it should be a sequence of these things. It turns out it doesn't look as pretty and then it doesn't go with the metaphor of a cube of meat. It's fine. But we need 140 of these sort of pieces of shot data, laid out in the same way and in the same order. And then we feed it to our network and we ask it basically, hey, if I were to show this sequence to a juror, what is the likelihood that I would get a conviction? All right, so I spent a bunch of time early on talking about how I can't talk about cheating because, or can't talk about anti-cheating because it makes it less effective. And then I spent 35 minutes talking about how this thing works. So did we just light the whole thing on fire? Good news, the answer is no. As you guys probably expect, this is not a straightforward linear process that we're doing with VACnet. It's actually a loop. We're going to just keep retraining this thing. And because we aren't replacing all player reports, we're only supplementing player reports, it means that VACnet basically identifies new cheats as players identify new cheats. So once a week, which is roughly the cadence that we have for retraining right now, basically anything that players have identified in the last week is new. VACnet gets a chance to go oh, okay, I don't know why you think that thing is cheaty, but I don't care because this is a supervised problem. And in order for me to get my cookies, I need to also think that that thing is cheating. So this process just goes on, and we've been really happy with it. All right, so let's wrap up a little bit here. So there's some sort of ongoing near-term work, as I mentioned. We currently, somebody basically, manually goes and searches their history for the training command, and then they run that training command, and then we retrain. It takes about 6 hours, and then we verify the model is better, and then we deploy it. We think that that should just all be automated, and we're working on that right now. We just want to say, hey, if you do better at convicting more recent cases, then you're probably the better model. There's also sort of work to be done around improving the learner with new models. We didn't have enough data for a really sophisticated model to begin with. At the limit, we were only dealing, let's see here, when we did our first deep learning run-ins, we only had about 300,000 points of data. And we have more now, but we think that we have enough to actually do a just different type of learner, where instead of sort of identifying what the features are, we basically just say, hey, here are a bunch of, here is a first-person narrative of what this player's game did. And let's take 8 rounds of that first-person narrative and decide, do I think that I would get a conviction from that? And we think that that'll be really great for attacking other types of cheatings, like the information assistance types of cheats. And also, we think it'll be a lot harder to counterattack. Well, getting some feedback from the mics. Finally, we want to generalize VACnet to other game modes, which we've started doing. We have a 2v2 competitive game mode that we started deploying in a few weeks ago, and that was awesome. We deployed in that mode, and cheaters didn't get the memo that we had done that, and so for like the first 3 days, we were just busting people left and right. Like the conviction rate was basically 100% for 3 straight days, because we had already chased a bunch of those players out of competitive, and they had moved over to this other mode. We are also basically generalizing VACnet to Steam. We're looking for partners for this. We expect that we have some early leads on that. Okay, so we should have plenty of time for questions, which is great. But in conclusion for us, we think deep learning is this sea change technology for sort of all of these evolutionary behaviors. And we think that the great thing about deep learning is, or one of the great things is like we can have these conversations with our users about cheating without just making it totally ineffective. We also think it's really, really good at catching cheaters. We're also applying deep learning to a bunch of problems at Valve, including just like anti-cheat and then Steam fraud. Dota actually recently deployed some some learners as well, like for hero selection, and the list actually goes on and on. These are basically resources that I can throw back up if people need help with pointers for deep learning things, but probably you guys have better resources than I do, so we'll just move on by.